Okay, welcome back everybody. In this video we're going to take a look at how to derive a state vector from a differential equation. As a reminder, we're on our third playlist in Kalman filter theory and applications. We did the understanding the equations, the heuristic introduction first, then we did taking the equations apart. In the second playlist, now in the third playlist, we're looking at state space concepts, and we're on the second video in that playlist. So last video covered the high-level concept of state space, and in this video we're going to talk about how to actually derive state space models from ordinary differential equations. And in the next video we'll take a look at examples of differential equations. And then we'll move on to difference equations, look at examples of them, the state transition matrix, and finally we'll take a look at some state space modeling diagrams. And the very last video and playlist will have to do with state space modeling in Python. Okay, a general nth order homogeneous linear differential equation can be expressed as a system of n first order differential equations. Let D denote the time derivative operator, with the exponents indicating higher order derivatives. Then this leads us to using an operator polynomial to express the differential equation. So you see this equation here with D to the nth power operating on y plus a sub n minus 1 times D to the n minus first power operating on y, and so forth. We set that equal to 0 because this is a homogeneous equation. Also, since this is a homogeneous equation, we can solve for d to the nth power on y, because that is primarily the differential equation. How do we do that? Well, we first set the variable x1, we define it to be the zeroth order derivative of y, in other words, y itself. And then the second state variable, x2 sub 2, we define that to be the first derivative of y, and so forth, until we arrive at x sub n, which is equal to the n minus first derivative of y. Then to get the differential equation, to make use of it, we take the derivative of each of those state variables. These variables are called state variables or states. And putting them together, we'll get a state vector, as we'll see here in a second. Notice that these state variables are merely definitions at the moment. But as soon as we introduce the derivative of the nth variable, then we'll see the differential equation come into play. Okay, so let's take the derivative of each of those n state variables. What do we get? Well, by definition, the derivative of x1 must be x2, and so forth. Finally, when we take the derivative of xn, we can set that equal to minus a naught x1t minus a1 x2t using the differential equation and the coefficients. But now we can put it into a more compact vector matrix form like this. We can say that the derivative of the state vector is equal to a matrix A times the state vector x. How do we do that? Well, we define the state vector x to just be the state variables x1 through xn arranged as a column, and then we take build the matrix A in this way. The first n minus 1 rows just have ones in the respective column there to indicate that these are the definitions of the states in terms of each other, as derivatives of each other. And then the last row captures the coefficients of the differential equation. And this is called the companion matrix of the differential equation. If there is an input function u, and it's present via its derivatives, perhaps, then we can write x dot equals ax plus bu, where b is a matrix such that when you multiply it times the vector u, might be a scalar actually, but if you multiply it times the appropriate sized b, you get it to be of the same vector size as x, and then you can add them. All right, equation 4 expresses the system's state dynamics, how the state changes with time. Later, we're going to include white noise as an input, separate from the deterministic control input. But that's going to require that we take a look at stochastic differential equations. So we need to first get into stochastic processes, and then we'll look at stochastic differential equations. All right, to obtain the original output function y as a function of the internal state of the system at any point in time t, we posit that y is an algebraic matrix vector equation and therefore a function of x. So cx plus dut, where the matrix D is a direct feed-through of the input function u to the output y. Remember, y was the original variable we started with and had all the derivatives of that we used to define the vector x. So you can see that it's not hard to define y likewise in terms of some matrix C. Okay, the output equation is not a differential equation. It is an algebraic equation that represents a linear relationship between the instantaneous state x and the control vector u at time t and the output variable y at time t. You can think of y as the integral of the differential equation from the previous time t0 to the current time t. Kalman filter theory often assumes that the matrix D is in fact 0 and uses the measurement model instead of the output model. So there's another matrix M which when you multiply it times y will give you this measurement Z, measurement vector. So y being c times x, you can then multiply m times c, and then the matrix H is often used as for the actual measurement matrix. Okay, note that we haven't placed any restrictions on the size of the measurement column vector z. As long as H has n columns, it may have as many rows as desired. The repeated rows typically indicate redundant sensors. All right, where are we at? We've shown how to derive a state space representation directly from an ordinary differential equation. We've seen how to identify individual state vector components with the derivatives of the output variable. And we've taken a look at the measurement equation. Now, what are we going to look at next? In the next video, we're going to take a look at some examples of state space equations derived from various common differential equations. And as a reminder, there are Python scripts to play with up on GitHub. All right, that's it. Thank you for watching.